Um, Actually, if you look back into the progress of science, for the longest time, there are two major ways of doing science, right? You do the theory and you do the experiment. But the biggest development in the past few decades is computation come out to be the third leg of scientific research. And it's getting more and more so, right? I mean, I'm saying something obvious, but if you think better, I mean, science has been going on for several hundred years, right? But the past few decades, suddenly this came out. And then, of course, computation, there are different approaches and all that. And today, this morning, I see the drawings here. Professor Pitcher is talking about turbine combustion and modeling and all that. Now, one approach is the DNS, of course, direct numerical simulation. You don't do any modeling, you just go head on and solve the problem. So that turned out to be extremely valuable because there's no modeling assumptions, and it'll get more and more important, that approach, because the computer keeps on getting faster and faster and allowing to do that. And one of the leading researchers in this area is our speaker today, Dr. Jackie Chen. And she has just done some very, very original and very significant research in DNS of chemically reacting flows. I think for her, I've been working with her and learning from her since the 90s, right? Working together, yeah, from Hong Yin. And yeah. Right. So, two things impressed me. Is she is very bold. She is not afraid to go into new areas and the bigger programs. I think she holds the record of the largest computation civilian side of the computation in terms of, I don't know how many grids and all that. The other one, I particularly sort of really attracted me to her and felt fortunate to work with her, is that she does the computation, but also she's always interested in the physics, in the calculus, and she's always asking the important questions, the right questions. And then after, at the end of the day, you do all the calculations, spend so much time and all that. What physics do you learn? And that really distinguishes her as a really good computational person, a scientific computation person. So anyway, so today she's gonna share with us on cyber-combustion, and you'll see it's not just purely calculation; it's a whole range of things relying on the computation. So.
All right. First of all, I'd like to thank Ed for inviting me to speak here, do this lecture. I'm really thrilled to do this, and feel free at any time to stop and ask questions. As Ed said, Professor Law said, this is a talk on cyber-combustion, so it's a marriage between some of the high-fidelity numerical simulation approaches that we use in turbulent reactive flows, together with high-performance computing, both at the petascale where we're at today, and then looking ahead to the future where we're moving towards even larger computers in the exascale, exaflop range. So, first off, I'd like to just present an outline of what I'm going to talk to you about today. I'd like to first motivate why we're doing this work from a big picture perspective and why it's important. And then I'd like to discuss a little bit about the different types of research paradigms that we have. As Ed already alluded to, we have kind of this tripod of experiment, theory, and computation, and we're kind of at an interesting time now where all three legs of our paradigm are developing and at very rapid rates to where there's actually a good cross-section, intersection between the three different methodologies that we should be applying interchangeably and learning from these complementary approaches. Then I'd like to illustrate, we'll talk a little bit about direct numerical simulation approach, where, as Ed said, we resolve all of the fluid mechanical scales all the way from the integral down to the dissipative Kolmogorov into the bachelor scales, smallest scales. But however, it's not DNS in the sense of combustion, because you still have to insert models, incorporate models for the reaction kinetics and for the molecular transport and other multiphysics aspects such as spray or thermal radiation or other condensed phase types of multiphysics. So it's DNS only in the sense of fluid mechanics. What I'd like to do, time permitting, is to illustrate the different roles played by DNS through some examples of work we've done in the past few years. Not only to illustrate what's possible and feasible with DNS on supercomputers today, but also the types of analysis that you can do with them and how it can contribute to development of predictive models. Then I'd like to shift gears and talk about some of the more computer science aspects of doing this work in the way of mining large data, simulation data. I mean, it can be great if we could all use MATLAB and our sequential post-processing routines that we routinely use now, but for very, very large-scale data, you have to start looking at alternative ways to analyze and visualize and glean insight out of your data. It's like looking for a needle in a haystack when you have a petabyte of data to sift through. Then the second to last topic here is on a very recent co-design center that we are working on towards exascale computing where combustion is one of the key applications in trying to co-design both computer architectures, everything in the software stack from the application itself, down to programming models, to runtime systems, to execution models, and eventually down to the actual hardware, which will look very different, as you're probably already starting to see now with your portable handheld devices. There's a lot of accelerators and low power and multi-core and all those kinds of buzzwords that you hear about in the consumer industry, that a lot of that is also going to carry over to HPC, and it's going to become a nightmare to program, or to continue programming our scientific programs the way we do now for parallelism and scalability. So I'd like to talk about how we co-design combustion algorithms and computer architectures in the future. So, and then I'll just say the last few words about future outlook for this area. So let's start with the motivation. I'm sure most of you here have heard this already, but why combustion? It's a century-old field. And why high-performance computing? Why the marriage of the two? And so, in a nutshell, overwhelming amount of our energy still, 83% of it still comes from combustion of fossil fuels. And this is likely to continue on well into this century. There's still, depending on who you talk to or read, there's still at least 50 years to 100 years of fossil fuels, fossil energy. And so it's our responsibility and our national goal to do this, to use what's remaining responsibly by reducing the greenhouse gas emissions by 80%. There's legislation being mandated by this administration to reduce greenhouse gas emissions, CO2 and the like, by 80% by the middle of this century. And at the same time, to reduce petroleum usage by 25%, pretty near term, by 2020. And so that'll require huge increases in the fuel efficiency of the devices, practical devices that we operate and design, as well as being good stewards to our environment. So meeting this goal will require an entire new generation of high efficiency, low emission combustion systems. We need new designs for both internal combustion engines, gas turbines, both aero and ground-based, for power generation, and also burners. Sorry, I'm getting over a cold. And at the same time, we also need new fuels. We're looking at developing new biodiesel fuels, renewable fuels that are carbon neutral. And so some examples of this are engine designs that we're dreaming about, and maybe you guys will solve this problem, is how to design engines that burn biodiesel fuels efficiently for transportation, using some of the new novel concepts, and in particular some of the compression ignition concepts that have a potential for higher fuel efficiency than our gasoline spark-ignited engines. And how do you combine that optimally with fuel molecules that are yet to be designed? in the area of gas turbines for power generation, you probably can read about this in the news all the time about fuel flexibility. How can we burn not only natural gas, but also various other syngases and hydrogen-enriched gases in sequential burners? How do we deal with fuel injection processes when you have very different types of fuel molecules with very different types of physical and chemical properties so that you get high efficiency and low emissions? So these are some of the grand challenges that we face. And in order to do that, one important leg of this pedagogue for doing research is looking at petascale high-performance computing in our CFD of reacting flows. A lot of our current design methodologies are based on Reynolds average, Navier-Stokes, or URANs, unsteady RANs type calculations, and they're largely phenomenological. And we still have a lot of room to improve the science base that's needed to develop these new devices simultaneous with new fuels. And so we're hopeful that exascale computing and ever increasing, 1,000-fold every 10 years will help enable us to do high fidelity simulations, to see more, use this as a numerical probe akin to what you do experimentally with laser diagnostics. Let us see more, understand more, and then with that glean physical insight, incorporate reduced parameterizations into models that are much more predictive. And so a lot of the use cases for doing these high-end calculations are based on trying to increase our Reynolds number, which is the range of inertial to viscous scales and scales highly nonlinearly with it needs large amounts of computing power. We want to move up in pressure, and we want to move up in fuel complexity, transporting a lot more species and chemical realism. And so if you want to combine these three kind of orthogonal axes, it requires a lot of computing power. Just to amplify a bit more on this motivation of the changing world of fuels and engines, a lot of our fuel streams are rapidly evolving from our monolithic fuels, gasoline, diesel, and aviation jet fuel, to some of the more difficult to get to hydrocarbons, the oil sands, oil shale, coal, and various other renewable fuel sources such as the ethanol, biodiesel fuels, butanol fuels that you read about in the news every day. At the same time that the fuel streams are starting to evolve, there are also new engine technologies that are coming online, and some of these are more developed than others. Direct injection processes combined with homogeneous charge, compression ignition, combustion. I'm sure Professor Wright's talked about that in his lecture. And in general, the trend is going towards compression ignition with low temperature, higher pressures, more dilute fuels. And just to contrast the difference between diesel, gasoline, and HCCI, as you go from gasoline to both diesel and HCCI, you have less control over ignition timing and burn duration. You have a spark in a gasoline engine to determine when the fuel ignites, and likewise you have a fuel injection system in a diesel engine, but in a homogeneous charge compression ignition engine, you rely on isentropic compression to bring the thermochemistry to the point where the charge will auto-ignite on its own. And so there's a lot of care that has to be given in terms of how you prepare your mixture, thermal stratification, composition, EGR stratification, and so on, in order to get the desired timing and the desired burn rate, so as not to have everything go off, not to have your entire charge go off explosively all at once, which would end up driving a very noisy, knocking engine. And so because to get these greater efficiencies and lower emissions, we're going to lower temperature, leaner mixtures to avoid thermal NOx, to avoid unburnt hydrocarbon production, and to get higher efficiency, but you end up in a regime where you're fundamentally burning, combustion is occurring in mixed modes, mixed regimes, where you're not burning purely non-premixed, where the reactants, fuel and oxidase are segregated, and you're not burning in a purely premixed mode where the reactants, air and oxidase are fully premixed. But you're likely burning somewhere in between in a partially stratified premixed regime and propagating into a mixture that you think about it, may not be inert reactants, but might be actually partially oxidized fuel that's auto-igniting or has low temperature combustion occurring ahead of the flame, if there is a flame at all. So if it's dilute enough, maybe you're in a flameless combustion regime. But in any case, the current models and modeling strategy that we have are unlikely to work in these new regimes that we're targeting. And so, to make a long story short, we really need to get the right scientific underpinnings in order to facilitate the development of predictive, validated, multi-scale models. Just to give you an idea of the complexity for combustion inside of an internal combustion engine, it's multi-physics, multi-scale in the sense that it's temporally and spatially stiff. There's very disparate ranges of length and time scales, ranging from the cylinder geometry itself, which is on the order of bore diameters of about 10 centimeters, down to the range of scales where turbulence, mixing, and chemistry occur down here at the millimeter scale, down to some of the smallest scale phenomena occurring due to soot inception processes happening at the nanometer scale. And there's a comparable wide range of temporal scales where radical reactions are occurring on the nanosecond time scales on up to tens of milliseconds for slower kinetic processes like soot formation or NOx formation. And all of these kinetic chemistry, flow, mixing problems are highly nonlinearly coupled together, so you can't just treat them separately. Similarly, with chemistry, it's highly complex. To describe a practical fuel of interest requires large numbers of species and reactions on the order of, I should say, this is actually underestimated, more like thousands of species and 10,000s of elementary reaction rates. If you were to look at detailed kinetic mechanism, for example, for describing gasoline or one of the biodiesel fuels. It's also a multi-physics complex problem in addition to multi-scale. You have to deal with condensed phase liquid spray, everything from the atomization of, for example, in a diesel fuel injection process, atomization of the spray, dilute spray, chemical reactions and vaporization processes, gas phase kinetics, turbulence coupling, soot, surface reactions if you have a catalyst. And then you have also the input of thermal radiation, especially if it's coupled with processes like soot. And you have acoustic feedback a lot of times, also depending on the geometry of the device you're looking at. You might have resonances and instabilities due to the coupling between heat release and geometry. So a lot of these processes are tightly coupled. So in addition to internal combustion engines, it's also complex. There are also challenges being faced with combustion in gas turbines for power generation. And one of these issues is dealing with hydrogen-enriched combustion when you want to do pre-combustion carbon capture storage. And so I'm sorry this diagram is a little bit messy to read, but it essentially shows you an integrated gasification combined cycle for either gasifier for coal or reforming process for natural gas, where you separate out the CO2 in this upper branch here and form syngases through the water, adding steam and through the water gas shift reaction. You can separate out the CO2 and then compress it and transport the CO2 and bury it to capture the CO2. On the other side of this process, you end up with hydrogen once you separate the CO2, and then the hydrogen can be used, for example, in a sequential burner gas turbine to help with the efficiency. And there are all sorts of issues, and so eventually it goes through a gas turbine and you get steam and produce electricity from power. But relative to natural gas, hydrogen and various other combinations of syngases have higher stoichiometric temperatures. They have are much more ignitive, so they have very short ignition delays, smaller calorific values. They require higher volume flow rates to avoid of precious air and inert gases to avoid pre-ignition, and you want to ensure that flashback doesn't occur into your pre-mixer section. So unlike an aero gas turbine where you want to promote mixing and flame stabilization here stationary gas turbine, you want to do everything you can to avoid flame stabilization in a premixer section. And so you have to understand the differences in entrainment and mixing processes for hydrogen, which is a very light molecule relative to natural gas, which is more a Lewis number unity type fuel. And so understanding those mixing characteristics, their ignition characteristics, and flame anchoring characteristics is still a wide open challenge to making this type of technology work. And so I will later in my talk describe a couple of canonical cases that are amenable to DNS to help investigate flame holding and stabilization towards fuel injection processes in these types of applications. So, so to summarize, combustion science is absolutely essential for underpinning future technology if we're going to get there and do new designs and get things to market in a reasonable amount of time. It's already, high performance computing has really aided the aerodynamic, the airplane industry, so Boeing uses it on a regular basis, and I think our field, combustion, can also benefit from getting some more science into our models in our design tools. And so, as I've already said, regulations will continue to tighten in the energy industry and transportation sectors. We have to improve the efficiency. We need to decarbonize our fuel sources, and carbon capture storage is one way to do this. Our technology needs to respond to this legislation, and so I think research will enable both design improvements and also concept evaluation. So this next section is on research paradigms. As already stated, we really have experiment, computation, and theory working all together. And currently it's feasible to do very detailed measurements in laboratory scale flames, particularly at atmospheric pressure where you don't have optical access issues. It's open to having lots of laser diagnostics, doing non-intrusive measurements. And to a more limited extent, people are now looking at elevated pressure experiments inside of a spherical bomb type vessel, or looking at high pressure counterflow experiments, or spherically expanding turbulent flame balls, for example, that Professor Law is doing here at Princeton, and combining that with advanced laser diagnostics to make measurements of both not only the velocity but also scalar fields is critical. But still, even with that, you kind of have an incomplete picture. You're able to only make measurements of a few species, maybe not characterize the velocity and scalars together, but separately. And so you kind of still have incomplete information, and I think computation can fill in a lot of that gap by, in the sense that with computation you have precise control of the parameters. You can vary one parameter in isolation of another, where that's oftentimes difficult to do in an experiment. So if you want to really study causality, you don't want to change 2 or 3 parameters at the same time. You can do computations with the desired level of detail. If you only want to resolve the energy containing scales, you can do that with large eddy simulation or with RANs, whereas if you want to resolve the small scale physics or the full range of dynamics, maybe you want to do a DNS. You also have, with computations, the advantage of full specification of all of the boundary and initial conditions for the scalar and velocity fields, which is really essential if you want to do, use computation to help validate coarse-grained computation. So you don't have any ambiguities or missing information at the boundaries or initial conditions. It's also less expensive and less iterative. You don't have to cut metal. And so if you trust your computation and it has the right predictive ingredients in it, it facilitates a much faster design cycle. And so that's, if we wanted to actually meet some of these legislative goals in the next 10 to 20 years, we need to do a couple of iterations on our design cycle. And we need to expedite that as much as we can. Another observation is that compute power and numerical algorithms are advancing very rapidly, and that while we do have significant advances in computing and in experimentation and diagnostics, there's still always a need for theory. Good theory is always needed because you need to interpret your results. and it helps guide the right set of numerical and experiments and physical experiments. It helps with understanding scaling laws and for identifying reduced manifolds. Because eventually, we don't want to be carrying around 1,000 species in our design, large parametric design studies. We want to be able to rely on a way reduced manifold of the order of less than a handful of parameters, even with these complex kinetic kind of situations. So currently, I think predictive capability of these quantities of interest is still elusive, and so there's more work to be done. So just some considerations, computational considerations. Combustion in practical devices almost always occurs in turbulent flows because you have much more efficient mixing. It's both multiscale. We typically see about 4 to 6 decades in space and time in the scales, and it's multiphysics. I've already pointed that out through the IC engine example, but it combines fluid dynamics, molecular transport kinetics, multi-phase. And the governing set of equations that you have to solve, the Navier-Stokes equations, total energy, and species continuity equations, represent a tightly coupled nonlinear system of PDEs with high dimensionality, typically 5, 3 momentum, 1 total energy, 1 mass conservation, plus the number of species that you transport. And that can be anywhere from, in doing the DNS, from 10 to about 100 to adequately describe the range of fuels that we care about. So you might think of every primitive, at every grid point, you're going to have to possibly solve for 100 unknowns, primitive variables. So the computational cost quickly becomes extremely high. The spatial scales is just a summary of the spatial scales from turbulence, mixing, and flames. So from the fluid mechanics, the range of scales that you have to resolve if you're going to do a DNS are the integral scales, lambda. These are the energy-containing scales that are dictated by the geometry of the device you're in, down to the inertial range and down to the dissipative range, the Kolmogorov scales. And so the range of scales, turbulent Reynolds number scales as the ratio of the integral to Kolmogorov scales to the 4/3 power. And if you look at the number of grid points that's needed in 3 dimensions, you need the number of grid point scales as the Reynolds number to the 9/4 power, which is a daunting number. Similarly, for these gas phase type of kinetic turbulence interactions, the Batchelor scale, length scales for the scalar values are of the order of the Kolmogorov scale. So they're where the Schmidt numbers of order unity, not dealing with the liquid here. And then on top of the fluid mechanical scales and the scalar length scales, you also have chemical length scales dictated by which regime that your flame is operating in. So if you're working in a thin flamelet type regime, you can have flames that are 10 times as thin as the smallest fluid mechanics scale, Kolmogorov scale. So there you have another factor of 10 demand and resolution due to chemistry or flames. And so this slide just kind of illustrates this through the energy spectrum shown here with the K inertial range of -5/3 power spectra down to the dissipative end of the spectra. And so again, just repeating what I said, the number of grid points in a DNS scales is Reynolds number to the 9/4, turbulent Reynolds number to the 9/4. It's nonlinear. And let's see, some of this is repetitious, but again, the number of grids, number of species can be between 10 and 100. The typical methane air flame, if you look at the flame thickness based on its diffusivity and flame speed, is on the order of 10 to the -5 meters, so tens of microns. Whereas the Kolmogorov scale for a Reynolds number, turbulent Reynolds number on the order of about 10,000 might be a factor of 10 larger. And so that creates, exacerbates the number of grids that you have to carry to resolve all of the fluids and flame scales. Similar story can be made for temporal time resolution. In a compressible solver, you're limited by the Courant-Friedrichs-Levy CFL condition, and shown here are both the acoustic and advective CFL. You also have, on top of the convective restrictions for time advance, you also have chemical time scales based on flame time scales, that is the flame thickness ratio to the ratio of the flame thickness to the laminar propagation speed, or species reaction rates also give you a time scale. So you have to take time steps, smallest of those time steps to be accurately time resolved. Furthermore, in CFD, we have a range of types of calculations ranging from DNS to large eddy simulations to Reynolds average and Navier-Stokes. And in RAND's calculations, it's the least expensive of the three approaches. It's also the most inaccurate because you've averaged everything. You're not attempting to resolve any of the scales in the energy spectra. And LES, which is very important if you're dealing with cycle-to-cycle variations, you do resolve the energy-containing scales down to a cutoff, and then you presume largely, in our models today, we presume some sort of universal behavior for the unresolved subgrid scales, the filter that you have to model. And so it's necessary to still provide closure for the scalar flux terms, the combustion source terms. And so there's some questions as to whether that's this universality at the small scales is applicable when you have a reactive system, especially one that has large thermal expansion and dilatational effects due to heat release. And finally, the gold standard with and most expensive of these calculation approaches is DNS, where all of the continuum scales are fully resolved. It provides fundamental insight, and it provides also benchmark data to help validate some of the coarser grain models. So let's see. I just want to use this slide to point out from these three approaches that turbulence, on the one hand, is driven by large scales of motion. The turbulence time scale given by the integral scale and the turbulence intensity, and knowing the viscosity, this drives the forward cascade. And this has we've gotten a lot of mileage from this in inert, non-reactive flows. However, when you have chemistry due to combustion at smallest scales that relies on molecularly mixing reactants down to the dissipative end of the spectrum before they can react, many of these couplings here are highly nonlinear, and many of them are highly exothermic, especially in premixed flames and in auto-ignition type phenomena. And so it's still an open question as to what the influence of the small-scale diffusive reactive system is on the entire energy, spectral energy transfer. Whether backscatter as opposed to just forward energy cascade plays a important role in combustion systems. And if it does, we have a lot of work to do in terms of developing Reynolds stress, scalar flux models that adequately describe this phenomenon. And so that's one of the roles that I think DNS can help us understand more clearly. So the area that I've been involved in is looking at gas-phase chemistry turbulence interactions. And basically this involves turbulence entraining, infecting, straining, and wrinkling a flame sheet, creating more area for burning. So increasing the surface to volume ratio. And then through the turbulence cascade, eventually the reactants are molecularly mixed, and these reactions are enhanced with mixing up to a limit. So if you mix too much, you're going to quench a flame locally, and if that quenching is pervasive, you can actually blow out combustion entirely. And many of these reactions are also, as I pointed out, highly exothermic. They create heat release at the small scales. And especially premixed flames, which have localized dilatational effects, they generate a lot of heat release locally. And auto-ignition, which through thermal explosion also generates a lot of heat release pinpointed locally. And these could potentially have an effect on energy transfer. And then the full two-way coupling is between heat release, dilatation, which reduces the turbulence intensity through density property changes, and as I said, could alter the spectral energy transfer. So now let's talk about DNS and high-performance computing. So if you look at combustion as multi-scale modeling in general, you have everything in this diagram of time versus spatial length scales on a log-log plot, the types of different approaches that we have in our field. So at the finest scales, you deal with quantum mechanics, and molecular dynamics, kinetic Monte Carlo type simulations of atomistic processes. And then bridging that is these continuum approaches, which I'll focus on today, the direct numerical simulation, large eddy simulation, and Reynolds average calculations. And with petascale computing power today, we can perform DNS either at the atomistic fine scales or in the fine continuum scales up to about 4 decades. So if you think about having a sliding window of 4 decades where you can see everything, but you can't resolve all of it, you can resolve portions of it, then you can think about doing DNS in different parts of this time length scale space. And with the DNS in each of these windows, you can develop new parameterizations that will help you eventually enable you to bootstrap information from the finest to the largest scales. So now I'd like to focus on the DNS, and I'd like to point out that without significant computer resources on high-end machines, none of this would be possible. And so Department of Energy and NSF also have been very enlightened in terms of making these big machines available for open science, whereas before they were a lot of machines, but they were kind of mission-driven and kept behind closed doors for mission type of work as opposed to open science. And so InSight is one of these programs, and we've been very fortunate to get on the order of 60 to 100 million CPU hours per year to perform some of these calculations. So I'd like to describe the solver that we use, starting with the governing equations. These are the compressible reactive Navier-Stokes equations. I'm not going to go over them. You have them in your notes. But basically, we solve the continuity, momentum, total energy, and species continuity equations in a conservative form. These are equations 1 through 4 shown here. We assume that the inert gas, typically nitrogen, is the bath gas, and enforce the constraint that some of the mass fractions has to equal unity. Typically, we assume a perfect gas, ideal gas state equation. And some of the relevant thermodynamic relations between enthalpy and temperature for ideal gas mixtures are shown here for the enthalpy and specific heats. And then some of the constitutive relationships that we require are for the stress tensor, the species diffusion velocities, and the heat flux vectors in the governing equations. And they are shown here in equations 10 through 12. You can get very complex with the species diffusion velocity, or very simple as well. You can assume constant unity Lewis number for all species, constant properties, or you can assume individual species, assign individual species Lewis numbers or mixture average properties, all the way to multi-component diffusion, but very expensive to evaluate molecular transport properties. In our work, we typically use, for cost effectiveness, and we typically use mixture average transport properties. And these expressions here just show the diffusion coefficients given in terms of the binary diffusion coefficients and the mixture composition. Okay, and then similarly for the heat flux vector, we have 3 components describing the diffusion of heat due to thermal gradients, where lambda here is the thermal conductivity, and we typically neglect the Dufour effect. And so this is the heat flux vector in the equation for the energy. And so in the last decade or so, we've written a DNS code at Sandia called S3D. It's based on higher order finite difference scheme, 8th order in space and 4th order in time. It's an explicit Runge-Kutta method. And we can incorporate everything from detailed reaction kinetics to reduced chemistry. And it has a capability to handle dilute sprays, optically thin and thick radiation, and also some empirical SIP models. It's been ported to all of the major supercomputing platforms, and does extremely well in the weak scaling limit. We've also incorporated a particle tracking capability into the code so that we can aggregate Lagrangian statistics. A lot of the phenomenon of interest that we care about, like extinction or autoignition, are best analyzed following parcels of fluid element as they autoignite or inflame. And so particle tracking or flame element tracking is a very useful diagnostic.
I'm curious why you went with the finite difference, finite volume.
Why we went with finite difference scheme?
Instead of finite volume.
Well, we wanted to get, we would have liked to have gone spectral for the greatest accuracy for the least cost, right? And so the next best thing in our mind was to go higher order centered finite difference that has some, if you plot the modified wave number versus wave number, we try to hug the spectral line to as high a wave number as possible. And so that's why we want the accuracy for the minimum cost. So we use very wide stencils, higher order, either previously we used compact pad A schemes that were 6th, 8th order accurate, but that involved a tridiagonal solve. And so for parallelism reasons, we wanted to stick with a centered finite difference scheme where you only had nearest neighbor communication. So it's efficient. Okay, so a little bit more about the numerics. I already said we're using a finite difference solve. Our geometry is as simple as you can get. Somebody that, John Bell, who's an adaptive mesh refinement expert, and they've written like 1 million lines of code for an AMR code compared to our measly Cartesian mesh code. And so he calls this DNS code the hello world of DNS. Because of its simplicity, but simplicity also, to my mind, equates to efficiency, or easier to parallelize. Okay, so it's a rectangular Cartesian mesh. We're in the process of developing a cylindrical coordinates code so that we can handle round jets more easily. Explicit 8th order finite difference in space, these are the references. Explicit 4th order 6-stage Runge-Kutta method, both of these by Kennedy and Carpenter. We use a 10th order spatial filter to think of it as alias de-aliasing so that we remove the spurious noise at the highest wave numbers. It's purely dissipative, it's non-dispersive. So you don't contaminate lower wave number information. Let's see. And then we, as I already pointed out, we resolve all of the relevant spatial temporal scales, be it fluid dynamic or thermochemical or acoustic in origin. And then we use this Navier-Stokes characteristic boundary condition, NSCBC, to describe non-reflecting inflow-outflow boundary conditions. And it's been worked on by, starting from Poinsot and Lilly's original work, by a number of groups of people to improve this boundary condition treatment. And then sometimes we're periodic in some of the directions if we're dealing with a slot burner or isotropic turbulence. We also have an ability to specify isothermal or adiabatic walls for some of our wall-bounded channel flows. So for parallelism, as I said, it's a fixed mesh. It's a trivial domain decomposition. So far, up until very recently, we've been using MPI for scalable parallelism. And more recently, in the last 18 months or so, some of my colleagues, Ray Grout, Ramadan Sankaran, and John Levesque from Cray, have taken S3D and hybridized it with MPI plus OpenMP, so that within a node, intranode, it uses OpenMP for threaded parallelism, and then between nodes, it uses MPI for communication, for parallelism. Cray, NVIDIA, and I forgot who the other vendor is, have developed a new compiler called OpenACC, which will ease, I think, for everybody, how we code some of these hybrid machines that have accelerators on them. So now these are, OpenACC has compiler directives that you can put if-def statements in your code to have the compiler tell it to perform certain operations on the accelerator. Before OpenACC, people have been coding directly in CUDA, which is a real nightmare. It's like coding in assembly language, to actually, and transposing all of your array structures to move parts of the computation off to the GPUs.
I was wondering how you experience
we have a dilute point particle treatment, but it's fully coupled with the flow. Okay, let's see. So here we also have ideal load balancing. All the processes, this is a depiction of number of processes in our Cartesian mesh, all have the same amount of work, same workload. They do the same kinetics calculations. Communication is almost entirely nearest neighbor. We just communicate with ghost cells in our neighboring domains. And then we do a parallel collective I/O every so often, typically about every 500 time steps, to write out to disk or to perform some other analytics viz operation. We try to minimize that collective, any collectives that we have, because that slows the code down. Per node performance, we're currently limited by the memory bandwidth, and we're extremely scalable and portable on the Crays. I think now the XK6 is the most recent machine called Titan at Oak Ridge National Labs, the IBM machines, Blue Gene machines, and the Intel processors that are coming online for these accelerated processors. And so this just shows an example on some of, this is already outdated, but on the quad-core Cray XT5 at Oak Ridge, this is the cost in microseconds per grid point per time step in a weak scaling problem. So you just increase the problem size with the increase in number of processors up to 250,000 processors, 220,000 processors, and you can see almost a horizontal line indicative of ideal, pretty good scaling of the code. Okay, some of this is repeating, but anyway, we achieved a parallelism through 3D domain decompositions, where each MPI process has a chunk of the 3D domain. Same workload on all the MPI processes. Inter-process communication is only between nearest neighbors in the 3D topology. We tend to save up all the messages and do one large communication, and then use non-blocking sends and receives for communication. And all-to-all communications are only needed for diagnostic monitoring and for synchronization ahead of I/O. This is just to show the scaling that it's actually compute bound, and showing that the ratio of communication to computation scales is the inverse of the workload. And so it's mostly computation that we're computation heavy. We can't reduce the number of grid points per domain to less than 11 cubed because of our stencil width. This shows kind of the growth of DNS over the years since 1990 to present, and as a function of the number of grid points plotted on a log scale. And you can see that back in the 95 time range we had about 100,000 grid points. At that time, we were restricted to reduced mechanisms on the order of four species, transporting four of those species, and we could only do turbulence in 2D. So if you either picked doing full 3D turbulence on a 64 cube grid, which is very low turbulence, with no chemistry, or one global step in constant properties, or you pick detailed, or somewhat detailed, reduced chemistry in 2D. So neither of which is optimal because turbulence is inherently 3D. And so in time, we've progressed to where we can actually perform 3D turbulence with reduced mechanisms for everything but hydrogen. Hydrogen, we can do detailed chemistry, but for natural gas and for ethylene and larger fuels, we're looking now at transporting on the order of 2 or 3 dozen species, maybe as high as in heptane with 60, 70 species. And our biggest computation on the petascale machines now has got 7 billion grid points. And respectable Reynolds numbers, I think our turbulent Reynolds number there is now on the order of about 1,000, which is near to what turbulent Reynolds number is in an internal combustion engine. Just having dinner with Rolf Reitz last night, we were computing what turbulent Reynolds number in an IC engine might look like, and it looks to be about 1,000 to 1,500. So we're not out of range. We're not so low that it's irrelevant. Okay, so what are the roles of DNS? So first and foremost is to glean fundamental insight into these turbulence chemistry interactions in simple configurations. Second is to help provide both a priori as well as a posteriori evaluation of models for RANs and LES. Another use of DNS is to help evaluate experimental assumptions. In experiments, typically you have measurements either at a point along a line or at most in 2D. You can do planar measurements, but it's very difficult or impossible to get 3D measurements. And so you have to make a simplification, and we can use DNS to understand what you lose when you go to reduced spatial dimensions in your measurements. We can also use DNS data to help understand surrogate measurements. So for example, it's hard to make scalar dissipation rate measurements with mixture fraction, and so a surrogate that some of the experimentalists are using is thermal dissipation rate. So how similar or different are the spectral characteristics of thermal dissipation rate compared with mixture fraction passive scalar dissipation rate? Another use of DNS is to help evaluate the performance of chemical mechanisms, reduced mechanisms in the presence of both turbulent and molecular transport. And so you can imagine that you would traverse a much wider range of thermochemical parameter space in a turbulent environment than you would in a 0D or 1D more simplistic environment that we currently validate our mechanisms against, like a well-stirred reactor or a laminar premixed flame. Another point I'd like to make is that, and I think probably for those that attended Tin Feng's lecture last night, you probably saw this slide already, but basically it describes the chemical complexity that we're faced with for the different mechanisms that are out there. And he and Ed Law have categorized different mechanisms based on the time frame when they were generated, before 2000 up to stars representing since 2010. You see the trend is to go to larger and larger mechanisms in time. This is a logarithmic plot showing the number of elementary steps on the ordinate, number of species on the abscissa. And you can see hydrogen would be down here near the origin, and that as we move to the lower hydrocarbon species, ethylene, methane, DME, on up to some of the more relevant fuels for aviation and for IC engines and heptane, PRF fuels. A lot of these are from Lawrence Livermore, on up to large biodiesel fuels. You're looking at about several thousand species and 10,000 elementary steps to a detailed mechanism. And the other thing interesting to note is that if you draw this straight line through here, the number of species scales linearly with the number of elementary steps, where that proportionality factor is a constant of 5. And so this is impossible to incorporate anything but hydrogen or maybe syngas into a CFD calculation. So you have to reduce your mechanism. And there's a lot of techniques being developed for mechanism reduction. This is one of them. This is an automated systematic procedure developed by Tin-Fun Liu and Ed Law. There's a number of references down here at the bottom. But basically, they start with a very detailed mechanism, like I showed on the previous slide, of, say, N-heptane here at 500 species, and then through dimension reduction with directed relational graph, removing unimportant species and reactions. They can come up with a skeletal mechanism that's about 1/5 of that size. And then through further timescale reduction with quasi-steady state assumptions, and through diffusive species bundling of species that have similar transport properties, they can further reduce the number of transported species. And then Tin Feng has come up with an on-the-fly stiffness removal procedure in DNS methods, taking advantage of the diffusive transport timescales. And so in the end, we can actually incorporate something like an N-heptane mechanism that's accurately and efficiently described with 60 species and been validated against experiment and against the detailed model. And similarly for ethylene, from 70 down to about 20 species. And so they can come up with reduced models, mechanisms with a prescribed level of error and or accuracy, and give us time steps that are on the order of nanoseconds to about 1 to 5 nanoseconds that we can integrate our DNS with in an explicit solver. So that's a real enabler for us together with the computing resource. So now I'd like to switch gears and illustrate the role of DNS through some of the examples. We've created a number of benchmarks for model development over the past decade or so involving phenomenon kind of shown in these pictures here. Extinction reignition in syngas fuels and with ethylene jet flames. These are slot temporally evolving jet flames. We've looked at premixed flame propagation in structure under very lean conditions and also under stratified conditions for both methane air and now also for hydrogen air flames with and without NOx chemistry. We've looked at lifted co-flowing jet flames where the co-flow temperature has varied from being below to above the ignition limit, so that these are lifted flames that are anchored aerodynamically either in the hot co-flow due to auto-ignition or due to flame propagation or some combination of the two. We've also looked at homogeneous charge compression ignition in a very small volume, say somewhere in the bulk gases of an engine, and looking at low temperature ignition, NTC type, negative temperature coefficient type ignition, coupling with the mixing and isentropic compression processes in HCCI for fuels like DME and for N-heptane and most recently for isooctane. And I think Ankit, who's here, is also looking at fuels like ethanol and various ethanol gasoline blends. To get a picture, and the purpose of looking at these HCCI combustion DNS is to understand the mode of combustion. We don't know from engine experiments, what they're not fine enough resolved, and they're oftentimes chemiluminescence images that are line of sight type of measurements. It's very difficult to tell whether you actually have a propagating ignition front that's really just spontaneous ignition down a ignition delay gradient, spatial gradient, or whether you actually have a deflagrative balance between transport and reaction, like you would see in a spark-ignited engine. And so with tools like DNS, you can actually go in there and analyze what the mode of combustion is, what volumetric percentage of the heat release is burning in which mode, and how sensitive is the timing of ignition and the burn rate to mixture preparation parameters like the thermal fluctuation level, the stratification and temperature composition, or when you do direct injection, how many injections you do, and so on. So mixture preparation coupled with ignition kinetics, low, intermediate, and high temperature kinetics is important. Another class of problems that we've looked at in detail is hydrogen and flames propagating near a boundary layer. And so this is a very important problem in gas turbines burning these syngas type fuels, where if you have hydrogen, which is highly mobile relative to heat in other species, could find itself close to a fuel injector in a low velocity region where it can propagate rapidly upstream, and you wouldn't want that to happen. And so we can actually probe this by having a non-anchored premixed flame inside of a computational volume, and then feed boundary layer turbulence into this box and watch how that flame propagates upstream. And so we've discovered some interesting phenomena coupling between the heat release and the streaky boundary layer structures and pressure flow reversal in leading edges of the flame that can actually assist in helping the flame rapidly move upstream, which hasn't been seen before in understanding flashback. Another area, and finally this other area that we're focusing on is jets and cross flows. So this is an interesting canonical configuration for fuel injection processes, both in aero and stationary gas turbines. And I'll be talking more about how you anchor a flame in this configuration. So this is kind of the counterpart of the co-flowing jet flame. This is the cross-flowing jet flame. So I picked 3 case studies that I'll talk a little bit more in detail about. The first of which is a lifted turbulent jet flame in a hot co-flow second one is a turbulent jet flame in a cross flow. And the third one is a turbulent premixed flame in intense shear turbulence. And I'd like to talk on the third topic, I'd like to mention a little bit about the spectrodynamics of that. So let's focus on now on the lifted jet flames in a hot co-flow. And I'd like to show you illustrate the different ways we can use the data for analysis. And then, I don't know what has been the format. Do we stand up and take a break at some point, or do I just go on for 3 hours? What would you guys prefer?
Break.
Okay. Do you want to take a break real quick before we come back to this? Like a 5-minute break? Because it's been an hour. It's up to you. Or do you want to just stand up for a minute? What? Optional. Okay, so everyone wants to stand up where they're at and stretch their legs for 1 minute, and we'll start. Oh, Fortune 90 and F77. And then sometimes, I'll talk about later, we do a lot of our analysis now in parallel live.